Welcome back, game theorists. We are looking at sequential games. We saw how to solve them with rollback last time. Now we're going to look at how you can use rollback even when there is external uncertainty. So in some event other than the player's strategies influences the outcome. So we call it external uncertainty. The way we resolve that is to just take expected values. Once you've done that, you can use rollback just like you did in the earlier examples. So here's one illustration. We'll have two players. Like I said last video, I like to use some students in class, but I don't know you guys. I don't know who's going to volunteer, if anyone, so I'll just use some students from last class, back before the lockdown. Ethan volunteered a few times, so I'll have him be player one. And Ethan can decide to host a barbecue or not. Ethan, if he decides to host, can invite player two. Let's see, player two can be James. And James can either accept or decline the invitation. And now here's where the external uncertainty comes in. So if James accepts and the barbecue is going to happen, how enjoyable that is going to depend upon the weather. So let's say it's sunny with probability 40% and rainy with probability 60%. When I wrote these notes, I was in rainy Oregon, so those numbers were about right. But now I'm in rainy upstate New York, so those numbers still work. So the uncertainty, we model that as coming from a third player we call nature. In this case, nature really is literally nature, but more generally it can work for any kind of external uncertainty, whether or not nature is a source. We still call the uncertainty source nature. And now I got to list the payoffs. So I'll list Ethan's payoff on top. And I'll put James's payoffs on the bottom. So if Ethan doesn't host, I'll give them both a payoff of 0 because nothing happens. If James declines the invitation, I'll say Ethan gets a -1 because he's a bit unhappy about having his invitation rejected. If they have the barbecue and James accepts and it's rainy, that's not a lot of fun. Let's say it's -2 for both of them. Imagine your hot dog bun getting all soggy from the rain. Does not sound like a good time. If it's sunny though, that's great. They both get a payoff of +2. So if you try to use rollback here, we've got a problem because James has to decide to accept or decline, but he doesn't know what's going to happen. Our solution though is saying take expected values. So with probability 40%, it's going to be sunny. So we're going to take the weighted average of all possible outcomes. The weights are the probabilities. So probably 40%, we get a payoff of +2. Then with probability 60%, it's rainy, so payoff is -2 in that case. So 2 times 0.4 is going to be 0.8. 0.6 times -2 is going to be -1.2. That works out to -0.4. Now, in this case, the payoffs are the same for both players over here, so I had to do the calculation only once. If James and Ethan had different payoffs for the same outcome, then I had to do a separate calculation for each one of them. I had to find James' expected value and then also find Ethan's expected value. But here, they're the same, so only do it once. So now I'm going to rewrite this game, but I'm going to plug in that expected value. So Ethan moved first and can decide to host or not. James has to decide to accept or decline. I'll just write A or D without knowing the weather yet, but he does know expected values. And those work out to -0.4. Oh, excuse me, that's really for accept. So he declines, we said, the payouts for -10. And we said that was because Ethan was a little bit unhappy about having the invitation rejected. Okay, if he accepts, then we plug in these expected values over here. So we get -0.4, -0.4. So now we have rewritten the game with the expected values plugged in. So now I invite you guys to try to solve the game using rollback. So go ahead and pause the video here and think about it. Once you think you have an answer, press play. All right, I assume you've taken the time to work it out. So we said the payouts were Ethan on top and then James. Set that back over here. So rollback means we go to the end, figure out what happens there, and then work our way towards the beginning. So, because James's payoffs in the bottom, he looks at these two numbers, and he says that declining and getting 0 is better than accepting and getting -0.4. So James will decline the invitation. Ethan then realizes that if I make this invitation, it's just going to get rejected, so what's the point? It's better just not host in the first place. So the outcome is going to be not host. For the rollback equilibrium, we have to specify the complete strategy for both players. So Ethan plays not host. And then James is going to play decline. So same thing I was saying before, even though Ethan is not going to host, James still has a plan in case Ethan makes a mistake, ends up hosting, and James finds himself at this node unexpectedly. You're prepared for all possibilities when you specify your complete strategy. And that's how the equilibrium is defined. So here's a variation on the same game. So the way I set up the game originally meant that James had to decide to accept or decline without knowing the weather. Now, what if instead James could see what the weather was like first and then decide? Ethan knows the plan well in advance and sent out the invitation before he knows if it's going to work out or not. So maybe a week in advance, Ethan gives out the invitation, but James can decide at the last minute if he wants to come or not. So here's how we would model that. So we still have Ethan over here at the top, deciding to host or not. But now the next move is made by nature. This time it's going to be rainy or sunny. Same probabilities. And after that, James can decide accept or decline. And payoffs are still going to be Ethan on top, James on the bottom. So if it's sunny and James accepts, they're both happy about that. Payoffs are 2 for both. And we said that if James declines, then Ethan's going to be a little bit unhappy about his invitation being rejected. A rainy barbecue is no fun, so -2, -2. And again, we have the outcome where Ethan gets his invitation rejected. All right, so a similar setup but with different information because James can now see the weather before making a decision. So we'll do the same thing as before. We'll do rollback, but then we got to deal with the uncertainty by taking expected values, and then we will see what happens. So if you're confident you can figure it out, go ahead and pause the video here and solve it. If you're not so sure, probably still a good idea to give it a try, but we'll talk about the answer very shortly. All right, let's go over the answer. So we go to the very end of the game where James is making a decision, and James's payoffs are the ones that come second. So if James is over here, if it's rainy, James gets a payoff of 0 from declining and a payoff of -2 from accepting. Getting 0 is better. So James picks decline. If over here it's sunny and James gets a payoff of +2 from accepting versus a 0 from declining, in that case, it's better to accept. So now we go up one step further. We're at nature. We're here. Nature is deciding at random it's going to be sunny or rainy. So we got to start taking some expected values in order to resolve that uncertainty. So like I was saying before, EV stands for expected value. The payoffs are a little bit different here for each player. So I'll first find Ethan's expected value, and then I'll find James's. So probably 60% it's rainy, which means that James will decline. As a result, will be over here. And Ethan, whose payoffs come first, will get -1. So 60% chance of a -1 payoff. With probability 40%, it's sunny. James will accept in that case. Payoff is +2. So that comes out to -0.6 plus 0.8, which is +0.2. Now here we cannot appeal to symmetry because this path here is not the same for both players, so we gotta find the expected value for James separately. So probably 60%, it's rainy. James declines and gets a payoff of 0. With probability 40%, it's sunny. James says yes. Payoff is 2. So that's going to be 0 plus 0.8, which is 0.8. So now we write the game with those expected values plugged in. And what do we get? If Ethan does not host, both get 0. If Ethan hosts, then his expected payoff is 0.2. And James' expected payoff is 0.8. So now we figure out what Ethan will do at this node, and he figures that getting 0.2 by hosting is better than getting 0, so Ethan will host. So our rollback equilibrium is Ethan has one node, and he chooses host at that node. James had 2 nodes here, one for if it's sunny and one for if it's rainy. We said James will accept if sunny, decline if rainy. So that's how we deal with uncertainty. So let's stop the video here before my phone runs out of memory, and in our next episode we'll look at some other applications and extensions with sequential games.